So in the last class we saw the first integer factoring algorithm, which is called Pollard's row method. What it does is these 3 steps in green. It basically picks a function f. For example, you can take f to be x square plus 1, and it starts with a random x, applies f once iteratively and applies f twice iteratively. So you get a sequence x and a sequence y, and then in every iteration it takes the difference and GCD with n. So if this factors n, well and good, else you declare that the algorithm has failed. So what yesterday we showed, in the previous class we showed by Birthday paradox, that if a prime p divides n, let's say the p is the smallest prime dividing n, then in the square root pth iteration, step 2 will factor. So this is a square root p times log n time algorithm. Okay, and as an example of its success, this algorithm, Brent and Pollard implemented it in 1980, and they factored a big integer called the Fermat number f8, which is 2 raised to 2 raised to 8 plus 1. And they found 2 prime factors. So into 2 primes, (16 and 62 digits). Okay, so this is around f8 is a number of around 70-80 digits, and Brent and Pollard were able to factor this into 2 primes. One is 16 digit, other is 62 digit. 16 digit prime is this p that we used in the analysis, and since it is relatively smaller, so square root of this much time it took, which was around 2 hours in those days on an old UNIVAC machine. Okay, so it was quite fast for such a big integer. Okay, let us move to the next algorithm, Pollard's p-1 method. This will be different from the row method around the same time. This will do something different. Instead of assuming that p is small, it will assume that p-1 has small prime factors, so smooth. So it exploits the smoothness of p-1. For a prime factor p of n. So in the input, again you get an odd n, which is not a perfect power. In the output, you want a factor. The idea of this method is use the known prime factors of p-1 to compute a raised to p-1 roughly. okay, mod n. So the algorithm will do the following. So randomly pick an A and compute A raised to k minus 1 GCD with n. And k, what is k? K is this, basically it's a product of small primes. You don't, you will not know p minus 1, but you can still use the prime factors of it with maximum possible exponent. So you can use k to be r factorial, so product of 1, 2, dot dot r, and then raise it to a large enough exponent, let's say log n. Okay, so if you look at this a raised to k minus 1 mod p, since p minus 1 divides k, e raised to p minus 1 will be 1. Okay, so p actually divides d. That is the point of this step. So if d already factors n, then you succeed. So then you output d as the factor. Else the algorithm has failed. So you can go up to some big bound r. Okay, do this for all small r from 2 to big R. So let's take the following assumption. There exist primes p different from q, both dividing n, such that p minus 1 is R smooth. But q minus 1 is not. So this is the difference between p minus 1 and q minus 1. And using this, a raised to k minus 1 will factor in. So that is contained in this lemma. So with high probability, n is factored in r times log square n time. So as I said, the proof is fairly easy. You just observe that for this bound, when r reaches big R, what happens is p minus 1 starts dividing k, while q minus 1 will not divide k. Okay, which means that for every a in Zn star, e raised to k is 1 mod p, while for less than half of the a's, e raised to k is 1 mod q. Okay, so for all the a's, e raised to k is 1 mod p, but that is not the case mod q. So there is the difference. D will factor in. So time to compute a raised to k minus 1 mod n is O tilde log n times R log n. That's how big log k is. Yes, it's around R log n, and we could reach R by using binary search. So which implies that overall time is you will be multiplying not by R but log R. So which is O tilde R log square n. Okay, as promised in the lemma statement. So that's the bound. What are the successes of this algorithm, Pollard's p-1 method? So this is used in the great internet Mersenne prime search. So called GIMS. So in this international project GIMS, distributed computing is used to find prime numbers, and there the Pollard's p-1 method is used to weed out composites. Okay, let's move to the third method, Fermat's method. So Fermat method is something even simpler. What it does is it promises to factor n when p and q are very close. Okay, the two prime factors, or actually if as long as n has two factors which are very close, this method will factor in. So it basically uses this fact. It tries to write n as a difference of squares. And so basically iterate over n plus b square and take a square root. So it will vary b and try to and will check whether n plus b square is a perfect square, and if for some b this works, then you have a square minus b square representation, and which factors as a minus b times a plus b. So this works well if a factor of n is very close to square root n. If one factor is very close to square root n, the other is also very close to square root n, then the difference actually is relatively small, and it is the difference which this method will utilize. So basically, if n is equal to c times d, you can write it as c plus d by 2 whole square minus c minus d by 2 whole square. And if c minus d is small, c and d are very close, then you can find c minus d by 2 by brute force. So if c is extremely close to square root n, then d is also very close to square root n, which implies that c minus d is very small. So find it by brute force. That's the idea. So let's see the algorithm. Just a for loop. So for x 1, 2, so on, if n plus x square is a square, then compute its square root. And output y minus x. That's a factor of n, right? N is equal to y square minus x square. So it's a very simple algorithm. So its time complexity is m times log n. Where m is the difference between the two factors. Okay, so if the difference is small, then it's a fast algorithm. Based on this idea or this method of Fermat, Lehman actually gave a n to the 1/3 factoring algorithm for general n. So we will not discuss this, but you can read the proof online. It's not difficult. So using Fermat method, you can actually factor any number in n to the 1/3 time, which is slightly better than brute force, which is square root n. So more importantly, this Fermat method, what it is doing is modulo n, it is giving you two squares that are equal. Right. So this is the idea which other people have extended to larger and larger ring constructions, and that is what gives the most advanced integer factoring algorithms currently known. So the idea of finding two squares that are equal mod n, this gives more advanced algorithms. So, these algorithms are called Krejcik's family of algorithms. Okay, they are based on finding two squares equal mod n. So, let us take this idea further to show some famous advanced algorithms. So, consider this polynomial x square minus n. Okay, mod n, it is a square. Find numbers x1 to xk such that qx1 dot dot qxk is a square. Okay. So, now on the LHS qx1 dot dot qxk, this is a square mod n, and on the RHS, let me not define, let me just say that it is equal to a integral square. So, on the RHS, obviously you have a square. So, you have two squares that are the same mod n. They are both squares mod n and they are also same. So, that then looks like a square equal to b square, and you can hope that a minus b will factor n. So, this implies that x1 dot dot xk square is v square mod n. So, hopefully the GCD of x1 dot dot xk minus v with n factors n. That is the idea which is common to all these difference of square based algorithms. So, we will now look at some implementations of this, okay, concrete implementations. So, how do you, the whole game is how do you construct these squares, right. So, the first idea is by Lemur and Powers. It's a fairly old idea. They would use what is called continued fractions to construct these x1 to xk. So, compute the continued fraction so square root n. First find the integer closest to it, a0, then find best a1 such that a0 plus 1 over a1 is a good approximation for square root n. Then you go, then you add a fraction to a1, that should give you 1 over a2. Then you add a fraction to a2, that should give you 1 over a3, and so on. Okay, this is called a continued fraction, it gives you these integers, successively giving you a better and better approximation of square root n. And what is this representation good for? So if you look at the convergence, the ratios that you are getting, first is A0, next is A0 plus 1 over A1, third is A0 plus 1 over A1 plus 1 over A2, and so on. These are called convergents. It's basically a sequence of fractions that is getting closer and closer to square root n. So how close? E0, then this x1 over y1, which is A0 plus 1 over A1, then x2 over y2, which is A0 plus 1 over A1 plus 1 over A2, and so on. This sequence, okay, x0 by y0, then x1 by y1, then x2 by y2, they give improving approximations, rational approximations to square root n, and satisfy, they satisfy an amazing inequality, which is that if you look at xi square minus n yi square, then this number is at most 2 square root n. Okay, so kind of this difference of square, but there is an n weight here x. So if you look at xi square minus n yi square, this number is smaller than 2 root n in value. So this is a property of the convergence from continued fraction, right? So this is the deterministic process. You write square root n as a continued fraction, you find the convergence, and now you have these qi's which are smaller than n. It's in fact around square root n, and look at their product. So that product mod n is a square. So since these qi's are small, they are not very small, but they are smaller than the trivial thing, which is n. So since qi's are small, one hopes to find a subsequence I1 to Ik such that Qi1 to Qik is an integral square. And once you have this V, then you look mod n. So then this xi1 dot xik whole square is V square mod n. Okay, so you are in this situation of equal squares mod n, and then hopefully you will factor n. So this is the Lemur-Powers approach using continued fraction, but still this is not completely giving you all the steps, because you don't know how to find this I1 to Ik. Okay, so we'll see, there are several implementations of this. Let's see one. So Morrison and Brillhart's implementation, it's called. So this implementation will be will also give you an analysis, the time complexity, etc. It will be based on the, as promised before, it will be based on smooth number density. So this will actually focus on these, on finding these qi1, qi2, qik such that they are B smooth for a bound B. Okay, it will play with the smoothness parameter. So the idea is use these QIs that are B smooth for a suitably chosen parameter B. So let us see the algorithm, all the steps. So fix a bound B, function of n, consider primes up to that bound. So let's just consider the first B prime numbers. And so this is called factor base. Okay, so you have fixed a factor base, and every QI you will try to check whether it satisfies this factor base. So basically you look at the QIs that factor using just p1, that are PB smooth. And find B plus too many elements in the set. So you will be trying out QIs sequentially, Q1, Q2, Q3, so on, and you will pick those B plus too many that are PB smooth. That's the set S. Now look at the exponent vectors. So alpha I0 dot dot alpha IB for every QI in S. Let's call this alpha I bar. Now notice that you have B plus 2 vectors. There are, each has B plus 1 coordinates. So they will be linearly dependent mod 2. If you look at them mod 2, they are 0, 1 vectors. And since you have more vectors than there are coordinates, they will be linearly dependent. So pick the pick such a dependency. So compute this subset T such that alpha I bar in the subset mod 2. Okay. So what does that mean? So the above thing implies that now these QIs, if you pick from T, and multiply them, that's a square. So we have, this is how it finds these. So by picking PB smooth numbers, QIs, a lot of them, it finds a subset such that the product is a square. And once it has this, it will do the usual thing, the GCD. So product of xi for these QIs minus V GCD with n. So how do we analyze this? First thing we'll assume is that QIs are random. That's a fair assumption because it's a non-linear function. This is a random sequence. Assuming that, we will show that the previous algorithm in green, it takes time ln half square root 2, slightly more than square root 2 maybe. Okay, so this is the first analysis which is significantly better than brute force. Instead of ln 1, this is ln half. Like, that's the important thing. So how is such a thing shown? So again, this will be by smooth number analysis or estimate. So probability that QI is PB smooth this use the smooth number estimate, so you will get psi. Note that QI is around square root n, right? So up to square root n, how many PB smooth numbers are there? It is this. So which means, so how many QIs do you have to try to get B plus 2 PB smooth ones? So expected number of i's after which we get B plus 2 PB smooth QIs, this expected number is, so roughly B plus 2 times this 1 over the probability. So you get square root n divided by psi. How much time will the algorithm take? So the time complexity is dominated by the smoothness test. Which takes so already you know how many i's you will be trying, which is b times square root n by psi. For every qi, what are you doing? You are checking whether it's PB smooth. So you are dividing by P1 to PB, which is B divisions, right? So let's just multiply by B. So you will get B square times square root n divided by psi. That's the time complexity. So what is the B you should choose as a function of n, right? That's the remaining thing. So we will set B to be L square root n alpha comma C. To get B square times inverse of this probability, right? So it's a square root n 1 minus alpha by C. So this is the time complexity. Let's just fix alpha and C constant suitably. So this is what? This is by definition E raised to, so you are squaring, so in the exponent it is doubling. Plus 1 minus alpha by C right. That's the expression. So first you have alpha, then you have 1 minus alpha. Now this will be minimum when you set them to be equal. So which is minimized at alpha will be fixed to half, and then C also. Make 2C and 1 minus alpha by C equal, so C will also be half. So it will become exp log of square root n half times log square root n half. That's the exact, and which is so log square root n a half comes out with the square root. Right, so you get around 2 log n log n square root. Okay, which is L n half square root 2. That's the time complexity, right? Ln half comma square root 2. This is what you get. And B is B will be if you work out L square root n half, so you will get ln half comma 1 over 2 square root 2. Okay, so for that large a B, you will get similar time complexity. Okay, so this is the first integer factoring analysis you see. It's significantly better than ln 1. Now, what is the success story of this? So, this factored some large integers. For example, f7, this is the first example. So, this was factored into primes of 17 and 22 digits. And other 70-digit numbers. So, this is already quite something. This implementation of Morrison and Brillhart could factor numbers up to 70 digits. And this f7 is not that large, but the point is that it has prime factor of 17 digits. So, this is slightly more than what you saw before. F8 had a 16-digit prime factor. This is slightly larger, and it was factored first by this implementation. And this implementation used continued fraction of instead of square root of f7, it was 257 times f7. Okay, its continued fraction was used. So, quadratic sieve is a slight improvement over the previous implementation that you saw. Suggested by Pomerantz. So, Pomerantz suggested a sieving idea. To reduce the smoothness test complexity. So what he suggested is basically instead of checking each qi for PB smoothness, it would be better if you just divide all the QIs by PB and store the quotient. And also continued fraction method was removed. So there were two improvements actually. One is sieving idea, second is use qx x square minus 1 as originally suggested in Krejcik's family, keeping x very close to square root n. So qx will evaluate to numbers of magnitude around square root n, but instead of using continued fraction you just use this sequential growth of x. Okay, so this will give an improvement in the constant in the exponent. The square root 2 will go away. So we will get ln half 1 instead of square root 2. Okay, so let us quickly see the modified algorithm. This is a famous algorithm. So instead of the continued fraction and using the convergence, we have got the qi right before. Now you simply compute qx x square minus n for square root n and then square root n plus n where this big N is like before, it's b times square root n divided by psi. So you will get enough PB smooth number as shown in the previous analysis heuristically. So this is for x in this. These are the qx's you will get at these points. And then the smoothness, so that is one modification. Second was the smoothness test will be slightly improved. So for I1 to B, so the advantage of using this sequential x's is that once you find that pi divides the qx, you know the next place that will be divisible by pi. Okay, so you will only have to check n over pi, big N over pi many places. You don't have to check everything. That's the advantage we are getting in this sequence. In the sequence, that are divisible by pi. Okay, so you can find the first location and then the other locations are just by adding pi. And then you divide by pi. So the highest power. So in these places you divide by the highest power of pi possible in each place. Okay, so now in the sequence nothing is divisible by pi. Divisibility by pi has been removed. And now you will move to the next. This is a for loop, so start with p1, then move to p2 and so on. So in the end, the places where you have 1, these are the PB smooth numbers. These are okay, so you have done the smoothness, PB smoothness testing this way. So what is the advantage of this? What is the time complexity now? So time now is around 2n by pi in each iteration, and you will go 1 to b, which is n times 1 sigma 1 over pi. Now bth prime is around b size, b in magnitude, but since you are only summing over primes, this is actually significantly smaller. It's log b. Okay, which is n is, so substitute the value of n by psi. Which comes out to be L root n alpha c, if you substitute b to be that, times L root n so this is minimized at so if you again look at the calculation, so what is the difference with the previous calculation? In the previous calculation you had this square, right? Now you don't have the square. So alpha you will remain half, but c will improve. So you can check that it will become 1 over square root 2. Okay. C will previously it was half, now it's different. If you look at 1 minus alpha over c, this has actually so you get L root n half comma 1 over square root 2 square, which is around which is ln half 1. And b is ln half. Okay, so we have been able to remove this square root 2 that you were getting before. That's the advantage. So previously you were getting this ln half comma square root 2. The square root 2 has been removed. That's the improvement by Pomerance. Let's talk about the success of this. So this actually allows for this square root 2 has been removed. So it actually allows you to double n. Two-fold increase in the length of n. Okay, that is significant. So previously if you were able to factor 70-digit numbers, now you can factor 140-digit numbers. So that is what happened. So Lenstra and Manis, not very long ago actually, they factored 129-digit RSA challenge using distributed computing over the internet. It was the success. So you have seen till now factoring algorithm for ln half complexity. In the beginning I had said that the best known complexity is ln 1/3. We don't have time to finish that. That is done by the generalized or the general number field sieve. Let me just say a few words about the number field sieve and then we'll end the course. So this algorithm we saw works with x square minus n, right? So it is somehow related to square root n. So you can ask why just restrict to square root n? Why can't we go to cube root of n or n to the 1/4 or to general number fields, right? So that is what the number field sieve does. It goes to number fields. So Pollard suggested using algebraic number fields to factor numbers like x cube plus k, where k is small and x is large. And this suggestion was to use the number field where you are attaching cube root of k. So this idea was picked up, and Lenstra and Manus again improved the idea and then factored f9 2 raised to 9 plus 1. Right, this is the biggest Fermat number you have seen till now. So f7, f8, f9. This into 3 primes. Of 7, 49 and 99 digits. Okay, that is huge. So this is around 160 digit number, and it has 3 prime factors, 7 digit, which can be found by brute force, but then the remaining 49 and 99 digit prime numbers, they are really huge. There was no way to find this, but this something more complicated than square root n was used to factor it. So what is the idea of NFS? So quadratic sieve, what it is doing, it can be seen as using the norm let's call it n, which sends q square root n. That's a field, right? Q rational numbers attached with square root n gives you a field q root square root n. It's a quadratic number field, and the norm will map its elements to q as follows. So it sends x plus y root n to x square minus ny square. That's the norm. So this is the norm which was used. Ultimately, we actually fixed y to be 1, so x square minus n was used. And note that the norm of a product is product of norm. So if the product of xi minus, if this product of xi minus yi root n is a square, then the norm is also a square, right? So make it a square in Z root n, or in the, so if this inside thing is a square in the kind of the integer ring of the number field, then its norm will be an integral square. And right, so there is a chance of getting two squares equal mod n in this business. So it's a higher order generalization is to go to a number field. Let's call it K, by attaching an algebraic number alpha, which is realized as, look at the polynomial ring Qx and mod it out by a polynomial that is irreducible. Is an irreducible of degree d plus 1. And then use smooth numbers in Z alpha. Okay, so the smoothness is generalized from integers to extensions of integers called integer rings of the number field. And there again you only look at elements in this integer ring which are smooth. You can estimate their number like before, and if you have enough of them, then you will get their product to be square, and then you take the norm. That's the idea. Okay, but these details I cannot cover now because of lack of time.